In this video, we're going to talk about another concept related to velocity fields, the concept of flux. We begin with these two different fields that I want to imagine as velocity fields, exactly as we imagine them being velocity fields when we were talking about flow. A way to think about this is you can imagine you're taking some canoe and you're out on some body of water, and the vectors indicate, well, what is the magnitude and the direction of the water at any point. It gives you a velocity field for the water. Now, when we were talking about flow, what we did was we measured the degree to which the vector field aligned or was tangential to the curve that you were going. The degree to which you could just not paddle and your boat would flow along the surface of the water according to whatever the velocity of the water was doing at any given moment. And so we had seen that this integral was 0 where everything was normal, and this integral gave a value of 2 pi for the flow because everything was tangential. And I'm even going to go and draw on both of these a unit tangent vector at a specific point just to illustrate precisely what that t is. But now we want to change things up. Now we're going to move to the new concept of flux. And flux is the sort of exact opposite of this. Flux says, I don't care about the contribution of the field that is tangential to the curve. I'm interested instead in the proportion of the field that is normal to the curve. One way I like to think about this is imagining that my circle is a net, and I'm asking, well, how much water is going to flow across this net? In the spin field, where everything's going around in a circle, there's actually no transfer around that boundary. All the water that's inside just spins around inside. All the water that's outside spins around outside. But in this dispersion field, where everything's leaving away, well, as time goes on, the water leaves from the center and it crosses out that barrier. That's what I want to measure. That's my notion of flux. So I want to come up with some formula that describes this idea that I'm talking about, this idea of flux. So here's my equation. Let's ignore the preamble for a moment. The formula is the flux is f dot n ds, and that integrated along the curve. It's this particular line integral. This is almost the exact same thing as what we defined for flow integrals. It was just that flow was f dot t, the tangential component, and flux is f dot n, the normal component. Okay, so what about the preamble? Well, a few different things. First of all, I've just got my normal continuous velocity field with components m and n. And by the way, I want to be clear here that for both flow and flux, we're talking about two-dimensional vector fields, planar vector fields. We will talk about the analogous concepts in 3 dimensions later on in the playlist, but we're not doing it yet. Next up, if I focus on the n vector, okay, we saw that the n was the normal vector. However, at any point along the curve, there's actually 2 different normals in the plane, and we're going to choose the one that's pointing outward to our closed curve. Final point, this is one that's got really something new that I have to define in, is the concept of the curve. Okay, I say the curve is smooth, that we know, that just means the different components have a continuous first derivative. No big deal. Then it's closed, and we've talked about closed in the flow integral video. Closed just means it ends up exactly where it started. But the new word here is simple. So let me illustrate what simple means. Loosely, simple means there are no intersections of the curve, no self-intersections. So for example, this curve is simple because it doesn't intersect with itself at all. Whereas this curve is not simple because it just keeps on crossing over itself. If you have a whole bunch of intersections, then which direction is actually outwards or inwards stops being meaningful. And so I have to have this imposition of being a simple curve as well as the normal conditions of being smooth and closed that would be the exact same as what we saw for circulation. Okay, so our picture thus far is the following. I have one of my fields, I have my curve, I have my tangential vector, that's what we use to compute flow, but now I have this normal vector. Well, we have to do a little bit of work here because I don't want to leave my integral in terms of s. We see that integrals with respect to s, sort of the definition of the line integrals, were great for defining concepts. But if you have a specific parameterization R of t, you need a way to compute this. So the question is, how do I figure out what this normal vector n is in terms of a given parameterization? In order to solve this, I know that one way I can generate an orthogonal vector, a normal vector, given one that I do understand, like this tangential one, is to take a cross product. But cross products are things that only make sense in 3 dimensions, and I'm only in 2 dimensions right now. And so I'm just going to fake it. So let me just take the picture, and I want to go into 3 dimensions. So basically what I'm doing is I'm saying that everything I've talked about is down here in the plane, in the xy plane, but I'm just going to imagine I have a third dimension now. The vector field is two-dimensional, the curve is two-dimensional, but living now in 3 dimensions. Maybe you can just imagine having a 0 k-hat component, for instance. And then what I put up here with my animation is actually 3 different vectors. Okay, so first is t. T is this blue one, that's the tangential vector. We've seen that before, we understand tangential vectors. Then secondly, the k-hat vector is my green one. And I know what k-hat is. K-hat is a vector that points just straight up. It's a unit vector staying straight up in the z direction. Now, here is the magic. I can now get the normal vector by taking the cross product of these two things. What is the normal vector? Well, my normal vector surely should live in the plane, which means it's definitely going to be orthogonal to the k-hat. And we want it to be orthogonal to the tangential vector t by construction. And so, well, this cross product is going to accomplish exactly that goal. So basically, I've gone into the third dimension so I can make use of this cross product as this nice little tool for computing what a normal vector is to 2 other vectors in this case. I had to make up the k-hat as relevant. Now, I should note carefully here, my curve is right now counterclockwise when looked down on from above. If it was clockwise, then these 3 vectors would no longer obey the right-hand rule. So if your curve was a clockwise curve, then you have to swap this around and you have to do k-hat cross the unit tangent vector instead, and that would give the negative value. So there's a little bit of an issue with plus or minuses, and so what our convention is going to be is we're going to generally talk about counterclockwise curves, we'll call that standard, and then we'll look down on them from above and we'll use t cross k-hat. If you want to do it differently, that's fine, but you always have to obey the right-hand rule here, and so you might pick up some negatives to represent a clockwise rotated curve viewed from above. Anyways, what we've got is that the normal vector is the unit tangent vector crossed with k-hat, and now our goal is just to compute out what this is. The unit tangent vector was defined to be dr ds, and component-wise that means it's dx ds in the I-hat, dy ds in the j-hat, and because it is in the xy plane, 0 in the k-hat. Imagine my original curve was living down in the plane with no z component. The z component was just there as a sort of artifact to be able to do this computation. All right, so we've got a cross product. Let's go and do the determinant trick here. So I'm going to say my normal vector is, and I can take this determinant where I write the I-hat, j-hat, k-hat along the top, and then I write the t vector, and then I write the k-hat vector along the bottom. That's why I got the 0, 0, 1 along the bottom. Compute out this determinant, and you get dy ds in the I-hat direction minus dx ds in the j-hat direction, and 0 for the k-hat. All right, so we're done with the need for having a third dimension here. If you want, you can just drop off the 0 k-hat for the rest. For example, I'll just talk about my original field f, and I'll just write down its m and its n components. I mean, if you want to, you could write down a 0 k-hat as well, but at this point, let's just sort of forget the third dimension. All right, so now finally we have enough machinery to go and compute out what our flux integral was. So remember how it was f dot n? So let's do this. It is the line integral over the curve of f dot n, but my n is dy ds I-hat minus dx ds j-hat. So then I'm going to execute the dot product, and it just simplifies to the integral of m dy minus n dx. Basically, what I did here was 2 things. First of all, if I multiply the I-hat components together, for the field it's m, and for the normal vector it was dy ds, so those multiplied together, but dy ds by the chain rule we will define to be just dy, and then likewise for the other integral, the minus n dx. And so this is my final answer, and indeed my personal preferred format, the sort of differential form for computing out a flux integral. All right, so let's go back to our 2 different fields, and I'm going to compute out the flux for both of these, but let's sort of anticipate what it's going to be. For the field where everything is dispersing from the origin, the field is indeed exactly normal to the curve, so I can imagine a lot of flux across this boundary, and so I'm expecting to have a large positive number here. For the spin field, it's the opposite. There is no normal component to the field at any point. The field was always tangential, so I'm expecting to have no flux across that boundary. But let's compute it out. And indeed, I'll actually get you to pause and try to compute it. I'm going to do it very quickly in a moment, so if you pause and try to compute out the flux in these 2 situations, well, anyways, here's the answer. We parameterize in the same way. Our definition is that flux is the integral of m dy minus n dx. I plug in the m and the n, which is cos for the first integral and sine for the second integral. And then for the dy, I take the derivative of the y component, so the derivative sign, which is cosine, that's what happens in the first integral. And for the second integral, where I've got the dx, then I take the first component, which is cosine of t of my curve, I take its derivative, which is minus sine of t, and so I get this minus sine of t dt. Okay, there's two negative signs of these integrals, that adds up to just a positive sign, so it's basically cos squared plus sine squared, which is 1 for the integrand. So we're integrating 1 between 0 and 2 pi, we just get 2 pi. Okay, for the other, I'll just put it up on the screen, and you can walk through and verify that I've changed my field appropriately. For the spin field, I've got an integral of 0. So returning to my two vector fields, I'm actually going to put out the answers for both the flow, or sometimes we call it circulation when it's this full closed loop, as well as the flux. And what we've seen is for the one that everything is dispersing from the origin, there is no flow at all, but lots of flux. And for the one that's spinning around the origin, there's no flux at all, but there's lots of flow. And so, well, flow describes the tendency for the vector field to be tangential to the curve, so that you sort of just flow along with the vector field. The flux is indicating the degree to which the vector field is normal to the curve, in which case the vector field is sort of crossing over the boundary of that particular curve.